Yeah, so hello all. My name is Mike Lawler. I'm based at UC Irvine, and I'm a project scientist in the Department of Earth System Science. So I'm going to tell you about some NSF funded work that we're conducting this summer in the high Arctic on board the Swedish icebreaker ODEN. Basically, we're going to make aerosol composition measurements with the aim of trying to understand what the source of cloud condensation nuclei is in the high Arctic in the summertime. So to briefly motivate, why are we trying to identify high Arctic aerosol? Basically, it comes down to the energy balance and the role that clouds play in that energy balance. So we're trying to understand, since every cloud, which is influencing the radiative budget at the surface and the temperature and climate of the Arctic, every cloud droplet began life as some nucleus, a particle in the atmosphere. And so we're trying to identify in the Arctic environment what these aerosol are. And we're especially focused on the summer for a couple of reasons. One is that in this period, the clouds are play a more surface cooling role than in other times of the year. So when there's incident sunlight that they can reflect away. And also in the summertime, the aerosol sources are more local. So stuff that's going on in the Arctic, in the surface ocean, especially biologically, probably is playing a role in the aerosol formation and therefore the cloud formation and properties in the high Arctic summertime. So we want to understand what controls this aerosol population and how it may change in the future in a warming Arctic with lower sea ice extent, warmer temperatures, etc. So we view basically two main pathways to generate local aerosol in the Arctic. One of these is primary aerosol, so that's direct injection of particles to the atmosphere. So this can be bubble bursting at the sea surface, would be one main example. Apparent biogenic gels, so polysaccharide goopy material ejected from the sea surface has been observed in this environment. The other pathway towards what we call secondary aerosol is through the emission of gaseous precursors out of, for example, open leads. So individual molecules getting up as gases, undergoing atmospheric processing or oxidation to form condensable materials that then can form new particles. So we refer to this as nucleation and growth, or new particle formation. But whether there are strong enough sources of these precursor molecules in the Arctic is not really clear. But both of these mechanisms probably depend on biogenic material in the surface ocean in the Arctic. So what are we actually undertaking? I'm going to be part of the what we're calling the MOCCHA cruise. This will be on board the Swedish icebreaker ODEN this summer. So it's microbiology ocean cloud coupling in the high Arctic. So it's a joint US and Swedish cruise. We're going to be out for about 2 months, and we're going to spend 5 weeks of that time drifting in the central Arctic, moored to a piece of multi-year ice. And there's going to be a suite of measurements. It's going to be quite extensive, I would say, of aerosol, sea surface microlayer, ice and snow, clouds and fog, and we'll be looking both at the chemistry and the biology of these different fluids and interfaces. This is just a picture of the ODEN out in the ice some years ago. So to be specific about what we're going to be undertaking, we'll be bringing an instrument we call the TD-SIM. This is the thermal desorption chemical ionization mass spectrometer. And it's basically a special purpose built instrument for collecting size resolved aerosol and analyzing it for a variety of species in a relatively quick manner. So we collect ambient aerosol, heat it to volatilize it into a mass spec, and we can do this on the order of about an hour. So you get a pretty good, it's sensitive to really small amounts of mass. So we're able to use this to look at really small particles. So if we take, for example, this is a size distribution plot of aerosol in the Arctic that was taken, I think, in the last ASCOS cruise. And you can see, so time is on the x-axis and then the size is on the y-axis. And you can see a few hours into this time series there's a sudden increase in particle number in two of these modes, in this sort of what we call the Aitken mode at about 20 nanometers, and then the smaller nucleation mode. So the question is, what causes that? Is that a primary particle production? Was there some nucleation event? So we're going to try to address that. If we can look at the aerosol basically before and after in this mode of tens of nanometers, and ask the question, are these primary gels directly emitted, secondary salts formed in the atmosphere? Is there sea salt in here? And we can answer this question, we expect to answer this question of whether these particles are primary or secondary origin, and then ultimately ask what controls, so this will be in collaboration with other groups, we're looking at other parameters, what controls these production mechanisms, and how might we expect them to change in a changing Arctic. So thanks, that's what I had to say.
Thank you, Mike. Any really quick questions for Mike? Okay, I think Tennille joined, is that right?
Yes, I'm here.
Okay, great. So Tennille is our second speaker, and she's going to talk on IASOA activities related to YOPP, and hopefully she will tell you what IASOA stands for, because I don't remember the acronym right at the moment.
And Melissa, you'll run my slides for me?
Meredith, yes, I will.
Oh, Meredith, I'm sorry.
No worries.
Okay, hello everybody. Good morning or good afternoon or good evening, depending on where you are. And so what I'm going to talk about today is the concept of getting merged observatory data files for the Europolar prediction from IASOA. And IASOA stands for, you can see in our logo there, the International Arctic Systems for Observing the Atmosphere. And if you look at the logo and you can parse for a minute that the blue is the ocean, the silver is land, you can see we're looking straight down at the Arctic Ocean, and all those little snowflakes show where there are observatories in this consortium. Next slide. I'm going to assume that this audience knows about the Europolar prediction, so I'm not going to have, because that was part of this collaboration team meeting, so I'm not going to talk at all about what that activity actually is. And this is just our poster, literally our poster, where we kind of show what the IASOA consortium is all about. We have observatories in the consortium from all of the Arctic countries. The observatories are defined by the fact that they are collecting process level data, lots and lots of process level data. And it is more than just stations, which are collecting things that are just telling you about how the climate is evolving rather than why it is evolving. And you'll see that I've got a picture of the polar stern in the middle of the ocean there, because we're looking forward with this activity of actually coordinating in advance with the measurements that'll be happening during Mosaic. Next slide. So this WMO Europolar prediction has got, as they often do, many science plans and implementation plans and sub-documents. And so I was sort of reading through the verification plan, and they have in there where they say they are going to do supersite, multivariate, high frequency observations. And they're going to use these as an opportunity for model process evaluation. And if you look at the official YOPP web pages, they've got a projection of the Northern Hemisphere, and they've got S's where all the IASOA super sites are, with the addition of 2 sites in Canada, which are Whitehorse and Iqaluit, which they've actually asked to join the IASOA consortium. So we're going to have a full sweep in IASOA of all the YOPP, what they're calling super sites. Next slide. So there's a whole document that lists explicitly what the common set of model outputs is going to be. And the verification document implies to me that we're going to have a common set of observation outputs. And my reaction, I got actually slightly breathless at the thought, and it was like, holy cow, how are we ever going to do that? We've got measurements from a multitude of different instruments and sometimes redundant measurements of things like temperature, different ways of processing things. The modelers are going to have these nice, tidy files with all their variables in one file on the same time conventions and same units. And though I will comment that when I listen to them talk, them coming up with an output, a common output so that they compare within one another is also going to be difficult. So I'm just wondering how they think that they're ever going to be able to reach out into these observatories at different places, different institutions, different PIs, different agencies, and actually come out with a observational data set that they're going to be able to do work with in context of the model outputs. Next slide. So I consider that to be a truly holy plan. I have just a 5-minute presentation here, so I will just leave this slide up to go into the IARPIC archive, and you can read with all the different problems that we have with coming up with some kind of a common observational data set that can actually be used for the YOPP verification plans. And I think that the primary problem is highlighted down there in red, is that the data at the research stations or on ship cruises or for campaigns is typically intended to support individual lines of research leading to an endpoint of peer-reviewed research publications, which is not taking full advantage of the benefit of these data sets that get generated. Next slide. So I have 2 slides here. There's one here, and if we go next slide, there's a second one. And again, because of the limited time I have here today, I'm not even going to try to jump to all the attributes that we're going to try to put into these common model or these common observatory data files. But suffice it to say, we are going to try to get everything in there. And I would welcome from this community to read through these lists and comment on them. Next slide. And there's a link at the top of that page. And if you go there, there's a Google spreadsheet where we have started sort of mapping out exactly what these data files might look like. One of the key things is that regardless of what observatory it's for, we're probably going to have, instead of like an instrument mentor or an observatory mentor, we're going to have variable mentors. And I have seen online, like for instance, Matt Shoup is probably going to be our mentor for some of the cloud variables that are retrieved from some of the active sensors at the super sites that have radars and lidars and radiometers. I saw Ulla Pearson's online. He'll probably be one of the mentors for some of the surface energy budget terms. I don't know if Chris Cox is online, but he would do radiation. But we are definitely going to have a number of specialists that are going to be helping us put together these files. Next slide, and that's it.
Thank you, Tennille. Is there a quick clarification question for Tennille? Okay. Our next speaker is Greg McFarquhar from SAMS and University of Oklahoma, who's going to talk about the DOE COMBLE campaign.
Okay, can everybody see my screen?
Yes.
Yes, okay, well, I'll start then. So I'm going to talk about COMBLE, which is the cold air outbreak in the marine boundary layer experiment. This is an experiment that has been funded by the DOE program. So it will be taking place in the winter of 2020. And I'm listing our science steering committee here. And I wanted to point out that Bart Geertz from the University of Wyoming, he's the PI and lead scientist for this project, but there are a number of other of us as listed there who are also going to be participating in the campaign and also in doing a lot of analysis. Well, I don't think I have to well motivate the campaign for this group here. Obviously, the Arctic is important. It is warming faster than the rest of the Earth. But really, in order to understand why it's warming so fast and why it's warming faster than models can predict, we need to collect an integrated, comprehensive measurements under different specific regimes. And one area where we really don't have the data we need right now is that of boundary layer convective clouds. especially those over the open ocean, where they're quite common, say, off the boreal continents and also off the Antarctic ice sheet. The depth, size, linear, cellular organization of boundary layer convection, it's highly dependent on synoptic conditions, in particular things like the wind speed, temperature, and stability, and also possibly on the number of aerosols. So we need to make measurement of these properties and also under the conditions they occur, because they're quite poorly documented. And they're also in this gray zone for weather and climate models. And I also wanted to point out that there's a lot of synergy between COMBLE and other activities that are going on in the Arctic, which really makes it ideal so that we can make samples of a wide range in different places of factors that are affecting this boundary layer convection and cold air outbreaks. So for example, is obviously the MOSAIC campaign, the AC3, which are some aircraft observations planned by the Germans, and also our group, most of the COMBLE scientists have also put in a proposal to the National Science Foundation called CSER, which would collect aircraft observations at the same time as COMBLE. Well, I wanted to show you just a nice picture here. This is a MODIS image from the 17th of March, 2016, and it's showing the area where we'll be conducting the COMBLE observations. So when we're looking at cold air outbreaks, we'll be looking at the time period where there's, say, a lot of flow off Greenland coming down past over Svalbard and down towards Scandinavia. So during that time period, you'll see cloud streaks, say, that are being roughly aligned with the wind, which are depicted in the red color here. You'll also see MOCCHA periods are places where we have mostly open cells, as indicated in the blue color here. Then we'll also probably have some observations that'll be collected in closed cells of stratocumulus, as depicted in the yellow color. Also some transverse bands, as in the green color here. Also some mesocyclones in the polar lows. And then also, as we get closer to Scandinavia, we might also have some observations that are made with more of orographic enhancement. So the idea is here we want to make observations that will allow us to determine the properties of the clouds associated with the boundary layer convection and also the conditions under which they occur. So in terms of our core science objectives, we've listed about 4 or 5 different core scientific objectives. So for example, for the boundary layer convection and these cold air outbreaks, we'd like to describe the fetch-dependent mesoscale organization of clouds and the precipitation, and that will be looking at both linear and cellular convection. In order to understand the clouds, we're also going to need to make observations of the surface heat and momentum fluxes, as well as vertical profiles of things like temperature, moisture, horizontal winds, and turbulence. We'll have a number of remote sensors, which will allow us to get the vertical structure of clouds and precipitation. And we also want to look at aerosol cloud interactions and how the aerosol affect the clouds, and hence the dynamics and feedback on their evolution. So we need to look at sources and sinks of aerosols, including ice nucleating particles or INPs. And more importantly, we really want to focus on the role of aerosols in cloud processes and how they modify the radiative fluxes. And then we'll be looking at the influence of the above quantities in polar cyclogenesis and polar lows. And ultimately, though, we have a large modeling component on this project as well, where we want to use the dynamic, thermodynamic, and microphysical properties that are measured, and we want to use those to enable evaluation and improvement of, say, the representation of shallow convection in cold air outbreaks over the open water, so that we can improve these in weather and climate models by developing a process-oriented understanding of these quantities. So what we did when we were planning COMBLE is we took a look at a lot of different locations, trying to identify where the optimal location of this project would be. And here we'd be looking at things like the relative frequency of organized convective patterns, such as cloud streaks or cellular convection. So you're seeing a plot in the uppermost panel here, looking at the percentage of the time we're getting these organized convective patterns. And we also looked at the parameter M, which gives the difference between the potential temperature of the surface waters, and that at a pressure level of 850 millibars, And when it's greater than 0, it shows that we have cold air outbreaks occurring. And then you can take a look, you know, at these sites here where we're planning to collect our observations. We have a lot of blue color that shows we're having a lot of these cold air outbreaks in a location which is fairly easily logistically sampled compared to some of the others. I say it's easy compared to some of the others. It's really not that easy. So looking at our project, here is a map of northern Scandinavia showing where we envision that the sea ice extent might be for our project. This is looking at where it was on 1 March 2016. And the red circles designate the range of some of the operational C-band radars that are present in the north of Scandinavia here. So here's where the polar stern might be as associated with the Mosaic project. There will be a northern site of Ny-Ålesund here, which will have operational radiosondes, several profiling radar systems, and enhanced observations as part of the AC3E project. We'll have a central site here of Bear Island. This is not an easily accessible site, so you can't get large sea tainers on there, but we are going to request we requested some observations there. Mainly, we're going to have some radiosondes there and some lightweight arm probes. This will be combined with the X-band dual pole scanning radar from Met Norway and some profiling Ka and W-band radars from Cologne. And then we'll also have a southern site at Andenes, which will have operational radiosondes, C-band operational radars, and there will be also aircraft and logistics support there. And the arm request there is for the AMF-1, as well as the aerosol observing system and ice nucleating particles. So I'll finish off with this slide here, just showing what some of the instruments will be at Andenes. And sorry, I jumped ahead there, such as the standard AMF-1 instruments, which include a surface meteorological station, Ka and W-band scanning radars, Ka-band zenith radar, an ARRI, radar wind profiler, we'll have microwave radiometers, LIDAR, total sky imager, and distrometer, as well as the aerosol observing system. So I think in the interest of time, I'll stop there and hand it back to Sally.
Great, thank you, Greg. I also wanted to note the chat box in the Zoom. So I think Allison had asked a question about the Google Drive link that Tennille had mentioned, and Meredith has posted it there. So if you do have questions while the presentation is going on and you don't want to forget it, you can feel free to put it there in the chat. Any quick questions for Greg? Okay,
yeah.
Our next, oh, sorry, please go
This
ahead.
is Ula, a person. Just quick question. You know, you have all these nice measurements of the atmosphere, boundary layer and stuff. One of the heat sources is the upper ocean. And I assume you'll have some sea surface temperature measurements, but do you have any measurements in the, at least the ocean boundary layer to understand the heat content and how it may be changing with these outflow events?
Well, we don't, one of the things we had considered originally was trying to put it on, trying to do a ship-based deployment, but that really didn't work out in the time frame of Mosaic and the other patterns. So we're not going to have any ship-based observations. So we will mainly be having these observations that I'll go back to the map here, showing at the Andenes site, the Bear Island, and other observations here at Ny-Ålesund. But it would be very nice if somebody were to come on board and able to add some of those observations, because I agree that would be a very nice addition to the measurement suite here.
Yeah, I mean, you could consider something like AXBTs or something like that to at least get it during the aircraft flights.
Mm-hmm.
I had a question. You said it's going to be in March?
The exact time period, I'll just pull it up here. It will be, the duration is from 1 January to 31 May 2020. Because this is a mobile facility. These are, you know, facilities that will be put at these sites, and they operate for, you know, they can operate for a reasonable length of time. It's not like an aircraft campaign where you're very limited in the duration that you can conduct the experiment.
Great.
Okay, thank you. I think we'll move on. Greg, I think you have to stop sharing your screen.
Okay, I think I stopped.
Great, thank you. And our next speaker is Ron Farrick from the Office of Naval Research.
Okay, unmuted. Why don't you guys show my slides? So we have a department initiative, department research initiative to look at polar cyclones. And these DRIs are typically 5-year projects of order of $10 million total, with a little more money in the years when you go to the field. And so we get the support about 12 to 15 PIs on these things. And they're typically organized around a particular problem that we feel like the time is right to investigate this and have an impact on some of the other activities we're trying to accomplish. So next slide. Okay, so motivation, I won't talk to all of these, but they're here for you for the record. But polar prediction in the atmosphere is in its infancy. Polar specific aspects of NWP haven't been addressed. And the real problem is the skill of our NWP over the Arctic is worse than anywhere else over the globe. The errors are much greater up there. And that's a combination of inadequate observations, lack of understanding of key processes, and poor representation of those processes in the models. And the problem really requires coupled modeling, ocean, atmosphere, ice, land, and high resolution regional modeling. I think the mesoscale is important, and the details and the gradients near the ice age make you deal with lots of difficult things, high contrasts and fluxes, sensible latent heating, all this sort of stuff that we don't typically deal with at mid-latitudes and the tropics. So next. Our focus in this is going to be on the troposphere polar vortex, which dominates the circulation over the poles, the pole rather, and the polar lows and Arctic cyclones that are the downstream consequences of that large-scale feature. And these are short-lived, intense storms called things like Arctic hurricanes in the past. They're not well predicted or understood, and we really have large forecast errors at very short lead times. And we think there's feedback and interaction, multi-scale interaction between those and the troposphere polar vortex. So then teleconnection to lower latitudes degrades the skill of forecasts at mid-latitudes. So it's a little out of balance with our understanding of these flow-dependent teleconnections that come up from the tropics. We kind of understand these tropical influences pretty well, but we get surprised by things that propagate down to mid-latitudes from the Arctic. And so we need to get those represented better in our NWP models. This also limits the ability to predict ice. So the seasonal behavior of the polar vortex and the polar lows may explain a lot of the trend in annual ice cover. So you guys can read the rest. Next. So when I gave the presentation of the pitch for this initiative, it was on Monday, and this figure came out on Friday in the Washington Post. You guys have all seen this. So the ice extent in 2016 was sort of, it was close to the 30-year average, which is the gray shaded area there, and on the low end, but wasn't anywhere near 2012, which was the record low ice extent year, and then hit the button 5 times. So around the end of September, okay, so there's 4 wiggles in this curve of ice extent that was associated with 4 intense cyclones in the Arctic. And between the end of September and the end of October, this ice extent got kicked out of the sort of 30-year envelope and into record low territory. And so this is actually kind of stunning. And I was recently at the AGU seasonal ice prediction meeting, and there was something like 65 predictions of the seasonal ice extent, and not one of them caught this. So the point of this slide is, as late as the end of September, we had no idea that the following winter was going to be a record low ice extent, and none of our predictive tools were able to predict it. So the point is, we don't have predictability for this, and this is kind of an important problem for the Navy. So we're doing a lot of work in our other programs on coupled ocean atmosphere ice models, but the missing piece, in my view, is the atmospheric forcing. And if we can't predict these storms that hammer the ice, then we got to fix this problem, because then we can't force the coupled ocean ice models that are important for us. So next. Oh, and go ahead. So you guys know all about polar lows, what they typically look like, and they're poorly predicted. You know, they have large track errors. You know, would be something we use that term in the tropical cyclone business. So getting the position, getting the genesis. Often they fail to predict them at all, and often when they are predicted, they're under-predicted by very large amounts. So to me, the analog is that, say, 60% of the landfalling hurricanes arrived without us being able to predict them. That would be kind of a big problem. So that's sort of how bad things are up in the Arctic in terms of predicting these energetic storms. Next. And if you look at reanalysis and compare it to observations, even the best reanalysis fails to capture these. This is just an example of 29 observed storm, ECMWF 1.25 kilometer reanalysis only captures 7 of them, and even the best ERA1 reanalysis only captures 13. So our models are really missing these important cyclones, even in the best reanalysis. So we can't even go into the reanalysis and do climatology or anything like that, because I mean, our models just can't capture it. Next. This is just some theory about you know, what can lead to these things. It's the combination of position of the ice edge, the influences of terrain, and cold air flowing over these features. You can generate these polar lows in the presence of topography on the ice edge, but with no topography and no sharp ice edge, you don't get similar amplification to these polar lows. So that leads to the next slide, which shows that there's sort of a geographic, couple of geographic hotspots for these over the in the far North Pacific and in the Greenland to Scandinavian seas area. So you know, there is some influence of terrain, influence of ice edge, and a couple of good places where the storm tracks are typically more frequent, where we think we can go and base in one or the other areas and have a pretty good chance of making some observations of these storms. And one of the difficulties is they spin up fast, so we don't have the kind of warnings we have for tropical storm, which then becomes tropical cyclone and marches all the way across the ocean. I mean, we're going to have to be there and be able to jump on them pretty fast. So we don't have the predictability 6, 7, or 10 days in advance to really, you know, be able to deploy on, you know, from a stateside location like they do for hurricanes. So we'll have to be based somewhere where we can get to them quickly. Next. All right, so in discussions with our science team, we kind of think there's some observing strategies that make sense. One is to have aircraft with pretty long duration and ability to get the high altitudes to kind of look at the larger scale influences, study the troposphere polar vortex, and up there be able to fly high enough to be in the stratosphere and sample the entire troposphere. And then it might be helpful to have a second plane that can really go and attack the details of these Arctic cyclones, kind of in the same way that we do the process studies on hurricanes. So this is sort of an ideal and an idealized strategy. We haven't developed specific flight plans yet because the science team kickoff meeting hasn't taken place yet, but we'll be doing that next. Next slide. And you guys know about all the synergistic activities up there, and this was a slide I used just to say that 2017 to 2020 or 2018 to 2020 is the right time to address this because there'll be so many other activities going on through YOPP, Mosaic, COMBLE, and CSER, and all these other things, that there should be ample opportunity to leverage other activities and coordinate with the science that you've already heard about today. So it's a good time to get an aircraft up there that can measure the larger scale and be able to deploy directly to these Arctic cyclones when they develop. Next. So key science questions. I won't read through these, but I left this slide in so you guys could look at it if you want, and related both to the larger scale troposphere polar vortex and the polar lows. Next. So we had a broad agency announcement in 2017 announcing this DRI. Received 42 planning letters. Of those 42, we encouraged full proposals from 20 PIs, and in the end, we ended up with 12 funded. And so this just gives a list of the institutions and the PIs at each of those institutions. And in close collaboration with this will be the Naval Research Laboratory. They do both basic research, but also we're funding them additionally to do applied research to bring the whole set of modeling tools, global, regional, adjoint modeling, all those sorts of things to the field program. We're going to have a kickoff meeting on May 30th to 31st at NRL in Monterey. And this is where everybody will say, okay, here's my hypothesis, here's the things I want to test, and then we'll spend a couple of days trying to design a field project and flight plans so that everybody can meet their objectives and figure out how to coordinate activities. There's also a collaboration proposal to NSF for a project called Thin Ice, and Dave Parsons and Steve Cavallo were the PIs on that with help from a lot of other people. And they're proposing to utilize the NSF NCAR G5 and get NSF support for that platform to coordinate with our activities on the DRI. And that may be it. Next.
Right. So Ron, I think we're going to have to move on.
Yeah, the summary is just there for you to read it. So.
Okay, great. And all the slides will be available on the IRBIG website after the call. Thank you, Ron. Really appreciate that.
Okay.
Okay, so our last speaker today is Pat Taylor, who's going to talk about some NASA activities during YOPP.
Yes. Thank you, Sally. Let's see if we can share. And everybody see? Excellent. So good afternoon. So energy is really the currency of our climate system. Just like you can't buy or sell anything without money exchanging hands, the temperature can't change, it doesn't rain, sea ice doesn't melt or freeze unless energy moves around. As Greg mentioned earlier, and others have mentioned as well, climate change in the Arctic is really outpacing the changes on other places on the globe. And a lot of that has to do with the changes in the energy flows that are happening. Clouds strongly modulate those total energy input into the Arctic system. They're pervasive, and yet our global climate models are poorly constrained in terms of the clouds. As most of us know, in the Arctic cloud water remains liquid well below 0 degrees Celsius. The partitioning then between liquid and ice in these clouds has a very strong impact on the surface energy budget. State-of-the-art climate models struggle a lot with the ability to partition between the liquid water and the ice in these clouds, and then this influences the surface energy budget biases in the models, limits our accuracy of Arctic climate projections, and has effects on global climate sensitivity. However, we currently lack the understanding to improve these models, specifically the process level understanding of what controls the amount of supercooled liquid in these cloud systems. And we lack the available data in order to do that, especially in the central Arctic. So addressing these shortcomings and resolving these key processes and controlling Arctic cloud phase is the objective of the Arctic investigation modeling processes of aerosols, clouds, and transport. I know it's a mouthful, but Arctic Impact, which is a proposal that has been submitted to just 2 weeks ago to the NASA EVS-3 proposal. And again, I'm Patrick Taylor, a research scientist at NASA Langley Research Center, and I'm the PI on that proposal. So the next couple of minutes, I'd like to share with you a bit of the science motivating this proposal submission. If selected, the airborne campaign would take place, part of it would take place in spring and summer of 2020 during the YOPP consolidation phase, and would be focused on overflying with Mosaic during deployments. The cornerstone of Arctic Impact is the synergistic combination of airborne measurements with satellite retrievals and multi-scale modeling studies to help address this science, and that is very synergistic with the YOPP and the objectives of YOPP. So as I mentioned before, climate models have significant biases in the surface energy budget, and clouds are a very important feature of the Arctic system. Over the last decade or so, in particular with NASA satellite data, in particular CloudSat and Calypso, the active instruments, have provided us a more comprehensive picture of how clouds influence the energy flows of the Arctic. In particular, like this graph demonstrates, is that in wintertime we have a net warming of the surface, typically by clouds, but in the summertime we have this net cooling effect in general by clouds. But if you look at what the climate models show, which are all the other colored lines on this plot, you see the models are very much different from the black solid line, which is from our series data product, the surface, the net cloud radiative effect at the surface. So the solution to try to resolve these large discrepancies is to better understand, or provide a better understanding of the process level of the processes that are influencing these clouds. Models exhibit a major disparity in the amount of supercooled liquid. To demonstrate that point, if we look at the plot here on the left plot, this shows the amount of supercooled liquid fraction in a number of different climate model simulations for different cloud temperatures. So if we just take minus 20 degrees Celsius as an example, you can see these two different models show one produces 5% supercooled liquid at that same minus 20 degrees Celsius temperature, whereas another model produces 70%. And both of these are represent a significant disparity away from the Calliope observationally constrained estimate for minus 20 being roughly about 30%. On the right side here, it shows you that just the schematic from the Morrison et al. Review paper in 2012 showing just the large number of interacting processes that influence the amount of supercooled liquid water in these clouds, which is so important for the surface radiation budget and the surface cloud radiative effect. And it is trying so what this graphic shows is that it's important to constrain each of these different processes and variables. And this has been the guiding principle for our Arctic Impact measurement suite, the ability to constrain each of these. So resolving these discrepancies in models then requires an improved understanding of ice formation processes, the role of aerosols, and how the interplay between cloud scale dynamics, large scale advection meteorology, and surface conditions all play out. As one more quick motivational figure, these changes in the representation of model cloud phase has dramatic impacts on Arctic climate. So Trudy Soralmo provided these figures to me, so I just want to quickly kind of show these for you. Each of these different lines shows you the zonal average warming for a climate change simulation. I don't remember exactly which one, but each of the different color lines represents a different amount of supercooled liquid, with this blue line showing low supercooled liquid fraction and the red line showing high. And the control and the two calliope constrained version showing kind of a range of different amounts of supercooled liquid. Depending on the amount of supercooled liquid, the model warms the Arctic anywhere from 13 degrees Celsius up to nearly 20 degrees Celsius. Additionally, the bottom panels are showing the projected amount of summertime sea ice cover loss over the same simulation, where you can see again on the left is the lowest supercooled liquid fraction, on the right is the highest amount of supercooled liquid fraction, and then the two observationally constrained variables from Calliope actually show the largest differences in the sea ice loss, in that you have the largest sea ice loss under this second one here. So Arctic Impact has a number of synergies with the year polar projection, in particular the need to improve model physics and in cloud processes. The proposed Arctic Impact mission again does occur during the YOPP consolidation phase and would also align with Mosaic. Even if it's not selected, this in science is still important and needs to be addressed, and still overlaps with many of the YOPP activities and objectives. In particular, the dedicated reanalysis activities, hopefully, presumably more reliable reanalysis that gets built from this these YOPP data sets are more rigorous to do satellite, are better to do a more rigorous satellite analysis on. And with that, I'll finish up. Thank you.
Thank you, Pat. So obviously, when we were putting this call together, we got excited about all the activities that were going on and tried to put a lot of things in one call. So we do have a few minutes for discussion. So if people have questions on any of the things that people have presented, or maybe, things where they see synergies or overlap that they want to talk about, we will discuss as long as we can here. And then there's also opportunities to continue discussion on the IARctic webpage if people want to pose questions they didn't get a chance to ask during the call.
This is Ulla Person, and I had a question for Ron. Are you still on there?
Yes.
This seems a couple of things in your presentation. You were talking about the autumn 2016 storms, so that was all September into early November, and I agree that those are really interesting, and we need to look at those a little more carefully. Where were they, and were they on the European side, and were they really polar lows? I mean, to me, polar lows are what was shown by Greg, is the cold air outflow from the sea ice over the open ocean. Were these events really polar lows, or were they lows that were advecting in from lower latitudes and impacting the sea ice? Do you have any idea? Do you want to focus on the March, February timeframe, which Greg was talking about, or the autumn timeframe, the freeze-up timeframe, or late summer was also mentioned? So I guess I'm getting a little bit mixed messages.
Well, Steve Cavallo could probably answer the question better. I get a little sloppy with my jargon in the Arctic, and he likes to call them Arctic cyclones.
Right, and I agree with him. I think that's the broader term.
Yeah.
Yeah, I think that's right. I'm just gonna chime in. Yeah, I think it's the more synoptic scale Arctic cyclones, I think that he's referring to.
Right.
Right. And is that what was impacting the sea ice in 2016? I haven't looked in detail at those events, but I seem to recall hearing that they were occurring on the European side of the Arctic, not the Pacific side. But I don't know if anyone has looked at that in detail.
Yeah, I think it was on the European side, if I remember right.
Okay, so perhaps if those types of systems are what you really want to focus on, and the impact on the freeze-up process, sounds like the freeze-up time period, September into November, might be the time to be really
yeah, there's some differences opinion on when the best time to go is. Some people would like to go twice at different times. It all depends on what resources we can get and you know what we can afford to do. So
right.
With these DRIs, we don't pick all the science questions first and then have everybody submit proposals. We pick a science team and then put them together and have them figure out what's the best thing they can do, the best science they can do. And that's the purpose of the kickoff meeting that we're having at the end of May.
Oh,
and,
okay.
You know, if anybody else thinks they want to participate in that, send me a request and I'll forward it out to Jim Doyle. And, you know, we're happy to have people that are potential collaborators participate in that meeting.
Okay. So you were just kind of laying out the different possibilities there.
Right.
Okay.
You know, it depends what aircraft and what observation systems we can leverage.
Yeah, very much so.
Great, thank you.
All right, thank you.
Good. Any other questions or topics? So Brian Kahn had to leave, but he put a question in the chat regarding sort of a more general question about the use of satellite data in YOPP and wondering if there was a point of contact or a specific plan for use of NASA and NOAA satellite data. I don't know if anyone has any thoughts on that. It might be something we can put on the IRPIC page as a question.
This is a person again. I have other questions, but I don't want to hog the question. So
go for
I'm
it.
happy
Nobody
to
else
ask another question if no one else has. Should I ask one?
Go for it.
Okay.
Yep.
So this was for Mike Lawler, and I don't know exactly where the ODEN is supposed to be in this coming summer. I assume it's going to be again in August, if that's correct. And in particular,
yes.
The science issue you're addressing is an important one, but it's been tried a little bit before making these aerosol measurements, and it's very clear that getting really good boundary layer observations at the same time as your aerosol measurements. And also question, part of that question is, where are you making aerosol measurements? Is it just inflow from the 35-meter height on the ODEN, which of course represents really only the surface layer air, or are you going to be trying to get samples from the clouds themselves, which are often decoupled from the surface? So there's a couple questions in there, I guess.
Sure. Yes, that's right. It's going to be in August and September of this year. And to answer the latter question, which I remember better, so the observations I described of the basically size resolved nanoparticles will just be from this 35-meter inlet from the right on the ship. There are going to be other observations. There's going to be this so-called helicite and an additional balloon that they're going to use to take samples of both aerosol and cloud water from elevation. So there's a hope that we're going to get a little bit of size resolved aerosol composition data and ice nuclei concentrations from if we're fortunate above the cloud, but also actual cloud droplets from low clouds.
Are there any airborne?
I may have forgotten the rest of the question.
Well, no, you basically addressed the issue. Are there airborne measurements planned for the aerosols from aircraft, say, other than, you mentioned the kite supported measurements, but are there any aircraft involved?
Unfortunately, no. No, we won't have aircraft.
Okay, so but you have hopes that you'll get some actual samples from in the cloud that you can then run through your heating process to look at the composition. Is that correct?
Possibly. Those samples are taken for a variety of analyses. It's not clear how much of that I'll get for my own analysis.
Okay, I mean, that seems to be an important aspect if you're going to address whether they may be IN or not, which, getting back to Patrick's comment about the phase partitioning, that's an important parameter for the phase partitioning.
Yeah, I would say my technique, I'm not saying I'm going to be able to distinguish IN, but there are going to be IN measurements at the surface and in the clouds that will be done by different techniques. There's going to be a wide variety of aerosol composition analyses. Okay, all right, thank you.
Yeah, I should mention there, and Mike did mention, there's several other NSF funded projects as well associated with this ODEN campaign, and they're all, I think, focused on aerosol aspects in some manner.
Okay, all right, thank you.